Hello, my name is Megh Shukla and I am a first year PhD student at EPFL. It is my pleasure to present to you this paper, VL for POS. This paper talks about out of distribution and active learning. And to this effect, we believe that this paper is targeted towards two audiences. First, the researcher who is curious about a new technique of doing out of distribution for POS estimation, and second, for the engineer who is tasked with building robust data pipelines and is curious about POS estimation in production. The goal of active learning is to iteratively improve a machine learning model. Since our model is trained on a limited amount of training data, there are going to be scenarios where the model does not perform at its best. So given an unlabeled pool of data, we can choose which images to annotate such that these images, if labeled, impart new information to our machine learning model and thereby helping it generalize to more and more test scenarios. So active learning is a way of selecting queries for annotation, and there are multiple benefits of active learning. First, it reduces annotation costs. Second, because of smaller data sizes, it improves training time. And third, intelligently choosing a subset of data for labeling can also help reduce bias in our datasets. So let's talk about how we can do active learning in practice. So we have a machine learning model which we train on our servers using training data and is deployed to various end users. These end users are the ones that are facing real-time data. And since our model is trained on a limited amount of training data, there are going to be cases where our deployed models do not perform well on real-time testing data. So on-device active learning is a way of selecting data on the end user's devices and thereby choosing which data flows back to our servers and retrain our model and redeploy. So this is like a cyclical process. The challenge of on-device active learning is that although we have real-time data, we have limited compute available and our algorithms need to have a very low compute footprint. On the other hand, the traditional active learning paradigm assumes that we have access to a server where we have large access to compute hardware, but our access to real-time data is limited. And in this talk, we focus on-device active learning. In fact, there are a lot of methods that do active learning for human pose. So why do we need a new method? So as we discussed before, for on-device active learning, we need an algorithm that is real-time. However, many algorithms in literature, for instance 1, 2, 3, 4, they rely on constructing a graph and the interaction between m labeled and n unlabeled data points, giving a complexity of O, mn. Another method which is based on reinforcement learning. However, as we all know, reinforcement learning takes a lot of time for active learning and is not suitable for on-device active learning. Methods that are of interest to us are those that can run real time, and these are multi-peak entropy, the learning loss family, and uncertainty in computer vision. We focus on multi-peak entropy, which is intuitively defined in the paper, but we show that multi-peak entropy is a consequence of maximizing the likelihood of a pose. With VL for pose, we take a first principles approach to active learning for pose estimation. Active learning is all about increasing the spread of the training distribution. And indeed, if we need to increase the spread, can we identify and annotate out of distribution samples? We frame the out of distribution detection problem as its inverse. We first try to maximize the likelihood of our training data. So to do this, we have a skeletal model, and this skeletal model tries to explain the poses in the training data. For instance, if we assume that these three examples were a part of the training data, our parametric skeletal model tries to estimate parameters that maximize the likelihood of having seen these poses. And when faced with an out of distribution example, since the model has not seen this kind of pose before, the parameters that it learns fails to explain this kind of pose, and therefore we can identify out of distribution. So what does maximizing the likelihood over our pose mean? Say we are given an input image x, and here y1, y2 up till yn represent the end joints that form a pose. So once we apply chain rule, we can distill any distribution down into these components. Now how do we simplify this further? One way of encoding domain knowledge is through a skeletal model. And in this case, we let our Bayesian network be a skeletal model with simple parent-child dependencies. For any joint, at most one joint is its parent, whereas one parent can have multiple children. Using the Markov blanket principle, we can distill down this joint distribution into a product-wise decomposition between simple parent-child joints. Indeed, as we may have noticed, that our skeletal model is quite simple. However, our objective is that of out-of-distribution detection, and it is much easier than, let's say, post-prediction, allowing us to use a simpler skeletal model. Traditionally, maximum likelihood involves maximizing the parameters given a set of observations, and these set of observations usually involve fixed values of x and y. But what if we can model y as a distribution for a given x? Indeed, in the case of pose estimation, for instance, for human pose, we have heat maps that represent a particular joint. And this heat map is in fact a spatial distribution for each joint. So to accommodate for this spatial distribution, what we compute is the expected log likelihood and not the log likelihood, since the expectation allows for multiple values for y. So simplifying this gives us this particular equation. And there are two important takeaways. One, it involves the QBN term, which is the skeletal model. It determines how various joints combine together to make a pose. It also tells us about the confidence of the pose estimator itself, of a particular joint being located at a certain value. So this equation helps us combine both the joint level uncertainty as determined by the pose predictor, as well as the pose level uncertainty as determined by a skeletal model. Our choice of modality conditional relationship depends on the underlying model. If our model regresses 3D key points directly, we do not have a distribution over the output, since by definition 3D key points are deterministic values. However, if we are modeling these heat maps implies a spatial distribution over the output, and we approximate the spatial distribution by taking the local maxima of the heat map and taking the softmax over it. This is equivalent to computing multi-peak entropy. To model the conditional relationship, for the 3D direct key point regression case, we ask our auxiliary network to predict the offset. So given the parent joint, we predict an offset that helps us estimate the child joint. Such an approach could also be used for human pose, but this leads to issues since for human pose, we observe that the pose model has ambiguity between left and right joint assignment. And indeed, if the model is confused during the left and right joint assignment early on, this leads to averaging out the offsets, and we have observed that a distance-based metric allows for better modeling of the conditional distribution. We elaborate more on this in the paper. In fact, we ask ourselves a follow-up question. Since we are already computing the expected likelihood, is there a configuration of pose that the pose estimator does not select as the pose itself, but one that maximizes this expression? Turns out that a smaller local maxima, one that the pose estimator does not predict, but it explains the conditional relationships well, can also lead to a valid pose. And we look at qualitative results for this later on. Our goal is not to compete with pose refinement state of the art, but to show that simple skeletal knowledge can also allow us to explore pose refinement. Next, we look at how VL4 pose performs both qualitatively and quantitatively. So qualitatively, we can see that a likelihood has a high correlation with model performance. For images where the model correctly predicts the pose, we observe that the skeletal model can correctly identify the pose. It explains the pose well and has low variances. Whereas for images where the pose estimator makes serious mistakes, we observe that the skeletal model cannot explain the pose and each parent-child relationship results in a high variance. This holds true for both human and hand pose. Quantitatively, we show that for the task of active learning, VL4Pose performs better than most algorithms with low compute requirements. In comparison to high compute requirement algorithms, such as those based on graph and reinforcement learning, we observe that VL4Pose is slightly inferior but still competitive. We also show qualitative results for pose refinement through VL4Pose. The solid circles are the predictions of the pose estimator, whereas the skeletal structure is the outcome of pose refinement through VL4Pose. Whenever the pose estimator makes minor incorrect mistakes, we observe that VL4Pose has the ability to conduct pose refinement. This is because, unlike the pose estimator, VL4Pose also accounts for local maxima, and some of these local maxima can better explain the skeletal structure and hence are chosen as a valid pose. VL4Pose is about making the small things click. How far can simple domain knowledge take us? We get a lightweight and real-time active learning algorithm. VL4Pose unifies joint and pose uncertainty. In fact, we argue that a much more complex skeletal model can tackle three problem statements at once: out of distribution, active learning, and pose refinement. My name is Meg, and thank you so much for listening to this talk.